real-time reception and analysis of satellite data. And what that actually translates into, in my world, is high temporal resolution data. And I gotta admit, I never worked with high temporal resolution data before until I started working on volcanoes. This is 20 years ago. And I used high resolution data where you had data coming in, every 2 weeks, every 30 days, and you ordered it and it came in 6 months later from NASA or whoever you ordered it from. So at the time when I was teaching, I talked about AVHR, weather satellite data, the GOES satellite data, the geostationary satellite data. You know, at 1 kilometer and 4 kilometer resolution, I thought that was worthless. And because I was basically a geologist, interested in detailed things. But the economy forced me to start looking at other data sets. And once I learned something about high temporal resolution data, it became very fascinating what you can do. So I'm going to be focusing on some of these lower spatial resolution and higher temporal resolution data. And I'll have to use volcanoes as an example because that's what I've been working on for the last 20 years. And that's really where this field works quite well. Okay, so the outline of my talk then, find the buttons here. I'll give you a bit of a definition for the data, the need for data. Data type analysis is done, the processing analysis, the modeling, the other software tools, and the response time. Because if you get high resolution data and you're responding to an event, such as maybe even an oil spill or volcanic eruptions, you need not just be able to get the data, but you have to get the information out as quickly as possible. So, definition. Real-time data, I call it a data acquired, received, and processed within seconds to minutes of acquisition. Now, satellite data, it's not going to be seconds at all, because you have to finish the pass, you have to receive the data, you have to process the data into something meaningful to even view it, so it takes a few minutes. Seismic data is a good example of something that happens almost immediately, within seconds. We have a lot of seismic instruments in volcanoes, and that's easily processed. So it's important to remember that we're looking at things have to move really quick to be involved. The other thing that you have to remember is real-time reception of data is costly, very costly. You have to have a good reason to need it and to do it. And the neat thing about it is with real-time data, you'll be amazed at some of the dynamics that you can start to study in the environment that we have high temporal real-time data. So in the case of our studies and our work, we have, this is the North Pacific region. These are the volcanoes in the area. Volcanoes over here in Kamchatka, Alaska. There's more volcanoes over here in northwest US. It's about 150 active volcanoes in the region. Active activity detected daily into one of the busiest air routes in the world. Airports are few and far between. These guys have to have plenty of fuel. And if they have to change course and land, there's not many airports in the area once they get in trouble. So we've got to plan well ahead of time. Fuel is a consideration. The jets flying at 900 kilometers per hour, which approaches these volcanic clouds very rapidly. Pilots have to have a quick response for routing and to check fuel consumption. So anyway, this is the justification for it in our situation. Here's an example of some of the satellites that we receive in real time. This is AVHR. There's a series of 5 of them in orbit. This is the MODIS. This is the NASA satellite. There's 2 of these in orbit. Then there's a GOES West, and then there's a Mediasat, which is a Japanese satellite. And the European side, there's the European equivalent to those satellites, both in geostationary and polar orbiting. This is the one anomaly right here, ASTER. ASTER is a high-resolution, high spatial resolution satellite, but its temporal resolution is not that great. However, ASTER is pointable. And so we actually have connections directly to the USGS. When there's an eruption or the start of an eruption or an incipient eruption, we can notify them immediately through the network. They notify the Japanese, and the satellite's actually steered and pointed towards that volcano for us. So we get that data, and as long as it doesn't conflict with something else already set in the system. So that was an experimental one. It can't really be used operationally. So let's look at acquisition time. Remember, if you have real-time coverage and you receive the data in real time, but if you can't get the data over to your processing system and to your scientists, it doesn't do anybody any good. So, our first attempt at doing this, we used to drive from Fairbanks out to the NOAA tracking station, drive back, load the tapes into the system, analyze them. It took 7 hours to do all that. Well, we used that and developed that during the Exxon Valdez oil spill. And of course, in that case, it actually worked okay because oil moves pretty slow. It moves at the rate that ocean currents move. And so we were actually monitoring the movement of these ocean currents on satellite temperature data. But when it came to volcanic eruptions, 7 hours was unusable. I mean, just would have been through the clouds over the region and gone by then. So we found a way to knock it down to 1 hour. And the way we did that is that the data received by the station is transmitted to what's called DOMSAT, which is a geostationary satellite, and then retransmitted to the various national archives around the East Coast. Well, one of the stations here in Miami, which is the Hurricane Center, also received that data, and we made arrangements with them to acquire data for us and provide the data. Now, that knocked us down to 1 hour, but still 1 hour was not quite fast enough, and plus we weren't getting all the data we really needed because of bandwidth problems. So, eventually, we purchased an AVHR station, and after that a MODIS station. So now we drop things down to our total processing time, once the satellite pass is completed, down to 10 minutes. And that includes getting it through the system, radiometric correction, geometric correction, and other processing done, customized for volcanic eruption detection, and an analyst looking at the data and then calling AVO South, we call it, in Anchorage, which is the headquarters for communication, and alerts go out. And all that can be done, if we're on the ball, 10 minutes at optimum. Of course, if it happens in the middle of the night and nobody's on duty, then you have to wait till they get calls in to wake us up. So it's very feasible. Now, you probably are familiar with most of these satellites, and I was going to just point out the differences. The GOES system is geostationary. It's looking at the equatorial region. But remember, Alaska is way up here at the pole, and so when it looks at an angle up here, it looks obliquely at us. So we have to do some processing to correct for that orientation. And when you do that, you change the spatial resolution from 1 kilometer for visible, I think it's 2 kilometers, no, 4 kilometers for thermal. And when the time you get up to our region, it's about 2 kilometers and 8 kilometers spatial resolution, which is even worse in some cases, many cases, for example. MTSAT's the same thing, but when we look at the AVHR and MODIS satellite, these are polar orbitings, so they're looking straight down all the time. So the corrections aren't, the corrections really aren't needed, except when you look off to the left. These broad satellites, and then they all have a lot of spectral channels. These 5, 5, and 5, and of course the NASA satellites, the experimental one, of 36. All of those are used in analysis. This is what a typical GOES satellite looks like. You can see Alaska up here. MT satellite is an interesting shot. This is a readout eruption. You can see it popping through the atmosphere right over here. And through processing, which is done automatically in our system, this is geometrically corrected so that we take this equatorial view of the Arctic. Now we're looking at it as if it was a nadir view. For the polar orbiting data, here's a typical strip of polar orbiting data. It's about 5,000 or more kilometers long and 2,500 kilometers across. We get enough of that, we can actually make a mosaic in real time as data comes in over the region if need be. But what we do is we cut out pieces of the data to look for target areas. And this is an eruption of Akbach volcano in 1997. It's a lava flow showing up in thermal infrared. So what we end up doing is, because of the volume of the data received, the data was pretty voluminous to begin with. And with modern systems, you have a lot of terabytes of storage and things. You can handle it all. However, there's a lot of it coming in, and with the new satellites, MODIS and GOES-R and InPost satellites, where you can have much more than 5 channels per satellite, it's a tremendous amount of data. So what we do is we cut the region in what we call sectors. Each sector covers a series of volcanoes, and then we can kind of throw away everything outside of those sectors, because it's mostly water. Although we turned out we can't always do that, and I can show you later why. Okay, analysis. What do we detect? As I showed you before, this is a typical thermal anomaly showing up. As you see it pixel by pixel here at a volcano. This is often a precursor to an explosive eruption. So if we